So I'll be presenting a little bit on interactive data visualization, especially trying to look at spatial detail and details that are changing over time with ATL03 data, so the photon cloud data. And then after we're done with that, Wei will show a little bit more how to make nice static plots for your publications so that everyone has pretty pictures to look at in your papers. So just to get started with this, I dropped a little bit of links and information on the 2022 Hackweek Slack channel, just so you can find where we're at. So first of all, if you haven't pulled the data from the website, then this is the workflow with Git, is to copy this GitHub address, and then you can just open up a terminal in your Jupyter lab, and you go git clone and put that in, and then it pulls all the data. Most of you have probably done that, and if you have done that, you hopefully won't have to pull any updates because I haven't changed my tutorial in a while. So let's get started on this. The notebook that I'm presenting will be under website 2020, book, tutorials, data visualization, and then it's this visualization Earth Engine GEE map. So let's open that. So first off, I was hoping that people could, if possible, follow along to this, running the code while I'm presenting. This will only work if you have signed up for Google Earth Engine. If you don't have access to that, then it probably makes most sense to go to the web page and just stay on Zoom and follow my screen. All right, so if you only have one screen, then most of the time you can probably just follow me on Zoom. You will just have to first run the few cells where we're setting up all the imports and the Google Earth Engine initialization. And once that is done, you can return to Zoom, and only when I'm getting to the exercise 1, where we're hopefully producing some plots, everyone, then you can jump back into the notebook and you won't have to run any of the intermediate cells that I'm showing. So let's get started. What I'm trying to show here is how to load ICESat-2 data using the Open Altimetry API, so you don't have to do any logging in and downloading to get just some simple one track of data from ICESat-2, and then how to query Google Earth Engine for geospatial raster data that you can display along with your ICESat-2 data to put it into context, and hopefully that will help you understand what is going on. So on a higher level, I'm just trying to hope that people have a better appreciation for the spatial detail and beauty of ATL03 once we understand what we're looking at. So let's get started with this. This first cell is just a bunch of imports that we'll be using. Well, that is not great. Hopefully this works. Let's see. Okay, imports are running. So the second cell here is just a utility function that I've written myself, and this essentially implements a class of named data collector that will be used to get all of our information together from Open Altimetry and from Google Earth Engine. And then to authenticate Google Earth Engine, you want to run this cell. In my case, I should already have authenticated this. If you have not, then you will likely see something like this. So this just is Google telling you that you have to follow this link to authenticate Google Earth Engine. And this will take you to this screen where you just have to use your account to authenticate access to Google Earth Engine. You click allow, and then it gives you this code here that you want to copy and go back to your Jupyter lab and paste this verification code in. And once you have that, it should give you this success message, and then you should be all set to go. So let's say we found some data, in this case on Open Altimetry, some ATL03 point cloud, and we don't really know what's going on. So how do we get there? I have an explanation here. This is just for reference, so I'll just go through this really quick. This is the Open Altimetry landing page. And if you browse data here, let's say I'm interested in the Antarctic, so I change the projection to Antarctic, and I want to look at data availability for ATL06. So in this case, I was looking for January 16, 2020, and I also want to see imagery of the day off, so you can do this for Modis with this cloud button. And then let's see, I want to look at Nevelisen ice shelf, and so I've zoomed in here, and there's something funky going on, so I can select this region and then say view elevation profile. And now it gives me something like this. And there's this weird section here where ATL06 apparently cannot decide where the surface is. So what we can do now is to scroll all the way down and get to this get APL URL link, and we just click that, and now this was copied to the clipboard. And this gives us the access URL for the Open Altimetry API. So in this case, I could paste this into the notebook, just like this. So now this is the thing that I've actually just now gotten from Open Altimetry. And when I run this, this is just the data that I want. And in this case, I want to look at track GT2R just because that's where the weird stuff was going on. So now we can initialize this data collector class, and it just essentially pulls out the date, the track, the beam, and longitude and latitude limits of my bounding box. Alternatively, in this case, I could also specify those data and run this, and now it would generate the Open Altimetry baseline request URL for me. So how do we request that? In this case, I just have written a function that's request data, and now it gets, in this case, the ATL03 and ATL06 and ATL08 data. So now we can look at what's in our data collector object, and we see the data that we had before, but now it's also loaded the ATL03 and so on data into pandas data frames. So how do we plot this? I'm gonna just go through how to plot this in Matplotlib because I think most of you would be familiar with that. So first I could create just an empty plot, and then to plot the ATL06, I can access these variables or these columns in the data frame like this. So I just add this to here, and now here we see the section where something weird is going on. Can also add ATL08 just with a different line style, so we can see how it looks differently, and so on. And now let's add some photon data from ATL03. So now this looks kind of weird because we included all photons, but we're not interested in all this noise. So we can interactively zoom in. So we probably want to look at something like this here. So that looks much better. Now we have a better understanding. So there's apparently two different surfaces of photons. And we could also do this programmatically by just specifying some limits. This actually looks pretty much the same. And we also always want to label our axes. So this is the code for that. We want to add a legend. And then we can do all sorts of stuff that adds information to the plot. And so if we show the figure now, we have something like this. So now we have some really nice spatial detail of ATL03 data that this shows. Now, we want to save this to a file. So you can do this figure.savefig function. And I'm just going to call this myplot. And now I have a new data file that's called myplot in here. If we open this, it looks something like that. But that's not really publication quality. So we want to increase the resolution. So we could do something like 300 dots per inch here with the DPI argument. So let's do that. Now we should have a better resolution plot somewhere that just doesn't show up. But I swear this has a better resolution. Oh, there we go. If we open this, we get a plot that looks a lot better if we wanted to put this in a presentation or a paper. So I have wrapped all of this into a method of this data collector function just to make things easier. So in this case, you can return the figure by just calling plot data on the ICESat-2 data collector here. And this just spits out a figure that's pretty similar to what I had before. So we can wrap this all into a function. It's just plot data from Open Altimetry URL. And now we can get these URLs and just call this function and save it. And that does everything we've been doing before in 4 lines. So now everyone who's following this interactively, I would invite to do this exercise 1, and I'll give you a little bit of time for that. So essentially, if you know any data that you would like to look at, then it'd be great if you could find that in Open Altimetry, just paste the link here, and then just essentially run this code, and then share whichever figure it spits you out on the Slack link. And if you don't know where to look at, or if you're just a little bit overwhelmed by all of this, there's a few Open Altimetry annotations here. So you could click on any of these and look at this in Open Altimetry. And then all you need to do to get the data is view elevation profile here after a left click. And then you can get the API URL by clicking on any of these get API URL links. All right, I will give people a few minutes to try to do this and try to come up with plots. And I will just drop in the tutorial prompts a little thread where you could upload your figures. Run it. The one cell that you have to run before doing this exercise is this one that defines this function, because otherwise this this line here won't work. We are a little bit tight on time, so I might just continue here. is there anyone, if I could get some feedback, has anyone been able to run this code, or have people been running into problems?
I think Open Altimetry might be a little stressed out. It seems to be really slow.
Ooh.
Got a couple,
Okay.
couple images seem to be popping in there. Philipp.
Yeah, okay. We have a few people who have managed to run this. Sorry, I definitely did not give people enough time. Do you people see my Slack now?
We sure do.
Okay, perfect. So yeah, here's a few examples of code that came in here, and I certainly know this example because that was one of the examples I gave, and I don't know what I'm looking at in these other images. So let's find out. All right, so I will just go back to the notebook and just run a little bit of code that shows how to get more information now with Google Earth Engine. And if we have time later, I will have this wrapped up in a function as well, and then people can show their plots along with images that hopefully show what we're seeing here. So I'll first try to get some ground track stats. And here I'm just trying to do some math to calculate how long the ground track that we're seeing here is actually, because we have only seen latitude values, so it's valuable to know how long this is. So this is 11.7 kilometers long. So now we want to look at Google Earth Engine to get some imagery to help us put into context which data we're seeing here. So Google Earth Engine does have a code editor online, which looks something like that. But this one runs in JavaScript, and since we're all so comfortable with Python now, it would be nice to have all of this integrated with your Python scripts. So there is a package called GEE-map, Google Earth Engine map, and that just essentially helps with the API of Google Earth Engine to also show interactively the data that we're looking at. So we can initialize this map just with geemap.map, and then this just opens up a map here. Now, here I'm just turning this ground track from, I'm just using the latitude, longitude data from the ATL08 data. I'm specifying that this is in latitude, longitude projection, and then I'm adding this as a feature collection of geometries to the map. So now this ground track feature is just a feature collection. That's not very helpful, so we want to add this to the map, and this is still not very helpful because we don't see it. So now we can set the center of the map to the center of our ground track with this. And now let's look. Oh, okay, we were in Antarctica or Antarctica. So we are somewhere here in Antarctica. This is our ground track plotted, and we can't really see very much here. So let's get some more information by adding a base map with satellite data. So now this looks a lot better. We see that we are on some ice shelf, and if we look on the right at the layer pane here, we can increase the opacity of that. So we're somewhere here. The ground track has just disappeared because we plotted the base map over it. So let's add that back in. And so yeah, so this was our ground track that we've been looking at before over this Nevelison ice shelf. Now let's query for some, in this case, only Landsat 8 images first. Landsat 8 roughly every 5 days to a week returns over these areas and takes an image. So we want to put this into context. So we're looking at this Landsat collection 1 tier 2 data in this case, because that's the one place where Google Earth Engine right now has data. So this is now so we can open this as an image collection in Google Earth Engine, and we can query for how many scenes there are in this collection. This just shows an Earth Engine number, and that's because it calculates that number only on the server side. So we would have to use this get info thing. And now this actually takes a little bit longer to run because it turns out we haven't done anything to this image collection yet. So we're querying for however many Landsat data there are overall. So Google Earth Engine is now counting all the single scenes that it has. And this is some 900,000 scenes. So we want to narrow this down. So we create a geometry for our point of interest in Google Earth Engine. This is just the center, longitude, and latitude of our ground track. And then we can filter this collection by the bounds of this point. And now we can ask again how many images there are, and now there's only 500 left. So we also want to look at images that are around the time when ICESat-2 passed over. So in this case, I'm just saying I want to look at 15 days before and after this overpass, and doing a little bit of date time transformations, and then it spits us out that we're looking for data essentially all of January of 2020. And then we can filter this by date, and now we're left with 10 images. So that's much easier. And so we can also sort this by the time when these were collected. This just makes things nicer later. So we can get some information on this collection, and this is a Python dictionary. So let's see what's inside there. It has a type, bands, ID, version, properties, features. So features sounds good. Let's see what features are. This is a list of length 10. So a list of 10 things, that's probably our images. Let's just look at the first one of those, and there's type, bands, ID, version, properties. So you get all this kind of information. So we can, for example, look at the ID, and this just is a unique identifier in the Earth Engine catalog that refers to this image. We can also look at the different bands in this. So here they're called B1, B2, and so on. So these are the Landsat bands. For properties, it gives us all this other information. So there's a lot of information. You might just want to look through it for a little bit longer if you try to find something. And we can loop through all the features, and now we get the product IDs of all the images we found. And we can also access these images by their ID. So let's just do this for the first image. So this is an Earth Engine image, and we can add that to the map as a red, green, blue composite. So these are just bands 4, 3, and 2 respectively. So we're just selecting those. Now, if we go back to the map, this image should have shown up, and sadly, it's all cloudy. So that's not the greatest approach. We could also add even more images, and I won't go back up, but there would just be more clouds. So we kind of want a better approach for this. So in this case, I'm just looping through all these features, access the images by ID, and then add them to the map. And I'm creating a new map so we don't have to scroll. So these are our 10 images, and now they're all added to the map. The one thing that I've done is that I haven't activated the layers. So here on the right, it now has all the layers, and you could click through them and see which one is to your liking. So in this case, this 04 one looks really good, and it looks like there's some water on the ice shelf, and this might explain why our data looks so weird. So now you could go back and just copy this ID here out, because this was the image that looked good, and paste this back in here. And now we can download this image. I'm not going to go through the details of here, but there is a function that gives you a download URL for smaller requests on Google Earth Engine. So this is just this download link. And we can save that image as a satellite image. And now we should have a geotiff. Should pop up here on the left pretty soon. So now we've downloaded this and we can open this with Rasterio. And now this is a dataset reader from Rasterio, but we can very easily plot this in Matplotlib with the Rasterio plot function. And now it shows us this subsetted image that we've downloaded. And we can now add the ground track on this as well. Here we just have to reproject the ground track from latitude, longitude to the projection of this image. So in this case, we use the Rasterio warp module, and then we plot it on there, and we get this thing. So if we put it all together, I have a function, I've written a function that puts all this together to make this map called makeGEE_map. And this queries for both Landsat and Sentinel-2 images and creates a map. So you get something like this, and then again, you could go here into the layers and look which one looks good. You could also go into full screen mode like this. Oof. And now my computer isn't happy anymore. Yeah, so you could again adjust the layers and just see which image you want. And this one, for example, looks good here. So this is my notebook not showing up anymore. Okay, looks like, oh, there we go. And so there is now another function that I wrote that just puts the plots together based on this product ID that you found for the best looking image. And when you run this, it just wraps together both of the plots of the ICESat-2 data and the imagery, and really puts this data nicely into context. And I think we are out of time, but I invite you all to, when you find the time, to look at this exercise 2, where you essentially just use the Open Altimetry link from before and then run this plot data and map function, and then it should give you a plot like this for the data that you found earlier. And these should look something like these examples here that I've put into the use example notebook. So this was one of the examples that Bryony had posted in the Slack that showed this data. And if we add the image here, we see very nicely that we're actually looking at a rift in an ice shelf. So this is where the elevation drops off here, and also a few melt ponds that are on the side. So with that, I think I've already gone over a little bit, so I will let Weiji take over and show you how to make nice plots that are static for your publications.
Cool. All right, thanks, Philip. I'll start with sharing my screen. Give me a minute. Share the screen. Cool. So this will be the second part of the data visualization tutorial. And if you haven't already, so we'll be working in the same folder, the data visualization folder. And the path, I've just put the path you need to open in the Slack. So what you would need to do is to right click on the data vis 2d.py file. And then there should be like an open with notebook. And you should be able to see that sort of the notebook here. If you're following on the website, you can also go just to the website, and this will be like sort of the same content as well. Cool. And let's get started. So this is for making sort of maps, as in like a 2D map of like a study area. Usually like you would have this in like a poster or like a presentation, like when you want to have like an idea of like give people an idea of where you're working at. So to give an overview of what I'll cover, we're going to learn how to sort of plot basic like map elements. So like a base map, titles, axes, annotations, etc. We learn how to plot raster data. I'll be using ATL14, the gridded blind ice height data in this tutorial. And we'll learn how to pick the right scientific color map. So a color map that makes good sense. And we'll learn how to plot vector data. So things like points, lines, polygons. In this case, we'll be using ATL11 for this tutorial. And we can style it differently. So different like line thicknesses, different sort of like, so for points, you can have like different symbology plotted. And finally, we're going to wrap all of that up and then learn how to like export it into like a suitable format for your audience. So be it like a presentation or like a poster. Yep. So we'll start with importing the 4 libraries we'll be using today. So it'll be IcePix for downloading ICESat-2 data, PyGMT, which is a Python interface for the generic mapping tools. That's like a package that has been around for, I think, like 30 years or something. And this is like the nice Python interface for it. Then we'll have like real X-ray and X-ray just to work with like n-dimensional data. And you should have seen these in like the previous tutorials today. Just to make sure we're on the same page, you should have a minimum IcePix version of 0.6.2 and a minimum PyGMT version of 0.6.0. Otherwise, if that looks good, we're ready to move on. Oh, and just a note on layers. So when we're sort of making maps, a general rule of thumb is to have sort of the raster layers at the bottom and have your vector layers on top. So think of it as sort of like making a cake. You want to have sort of the dense cake layer first at the bottom, and then you have like the icing and the candles sort of on top, so that it doesn't, you can't really like you can't put the cake on top of the candles. Otherwise it's, you're hiding like, the decorations. And so we'll just pull down some data and we'll be using IcePix for this. So we'll set up an IcePix query object and find the data we want. So ATL14 in this case, this is the ICESat-2 gridded annual ice product. We'll set a spatial extent. So this is the extent just over Iceland. You can pick like another region depending on like, so if you know the lat long bounding box of where you want, you can change that here. And then we'll, just to double check that we've got the right area, we can use IcePix visualize spatial extent function. That just kind of shows, okay, the red is the bounding box of where we're getting. So if you click on the zoom, the wheel zoom thing, you can zoom it in and out just to see where we're kind of at. Cool, let me see. And Emily's just posted a nice cake photo on Slack. Very good. And just moving on. So, and with the IcePix query object, so the region Iceland thing, you can sort of double check that what product you have and the product version. So in this case, we're using ATL14, the version 1 product. And if you're more interested in how to do all of this in IcePix, you can go visit these like pages, these links. Okay, so we've set up the IcePix query object. Now we need to sort of get the data. First, we'll need to log into Earth data. So hopefully you know what to do by now. So I'll just use my user ID here, and then my password, and that should authenticate us to Earth data login. And this will download all the granules, the ATL14 granules we want to the temp folder. Okay, and while this is downloading, So an X-ray data set, which you probably know a lot about in the previous tutorials, is just like a nice way of organizing an XY data. So you have an X dimension and Y dimension and a Z value. So in this case, our Z values are elevation. Yeah. And let's just wait for that to download. This is gonna take a while. But yeah, we'll be loading. So this will download a netcdf file. The ATL14 is a netcdf file. And we can read that just with X-rays open dataset function. So you just pass in like the file name here, and that should read it into a variable called ds. And this will take, let's see, everyone's probably pulling data at the same time. So this is gonna go a bit slow. Give me a minute. Data is downloaded and is it gonna load? Okay, yep, so it's loaded. Next, once we've got this data loaded, so this data originally comes in the 3413 projection, so the NSIDC CIS polar stereographic projection. We're just gonna reproject it to 4326. So basically you have long coordinates rather than like big. So the original coordinates are in these like sort of big numbers here, X and Y numbers, but what we want is probably like long coordinates. So X and Y here represents longitude and latitude right now. And you can look at, we'll be plotting the H, we'll be interested in the H variable. So this is the surface height variable in meters above reference to WGS 84. And if you have more, like, yeah, you can just click on some of these, like the hamburger icon or the file icon here to sort of see what these variables are. And there's some attributes as well. So these are just like the metadata for the ATL14 dataset. And Ben Smith and Tyler should be in this Hackweek as well if you have questions about how to use this, about specific questions about this dataset. Anyways, moving on, we'll start. So these are just like all like numbers, right? We kind of want to see we'll turn the numbers into colors because it's easier to visualize colors. So we'll start making our first figure. So to start a new figure, what you would do is you would call fig equal pygmt.figure. This will start a new instance class, and this handles like all of the plotting stuff. So this is essentially like a blank canvas where you can add stuff to it later. And then we'll be using the fig.grd image function to sort of plot a grid. So our grid will be our Iceland dataset and just the height variable. And we'll set frame equal true. So this will set the map frame, just set the default map frame using pygmt. And I'll just show you like, and you call fig.show to see what the map looks like. So this is just in 3 lines of code so plotting the elevation, the ATL14 elevation, and we have some like X and Y sort of axis annotations labeled by default. Okay, cool. So to make a sort of map that people can sort of understand better, you need to sort of like label your axis, right? So we can do that. So let's modify the fig grd image or grid image call we had just now. So we're passing in the same grid, but this time instead of using frame equal true, we can give it a Python list and sort of set like different arguments. So we can set the x-axis, we want it to label it longitude. The y-axis, we want to label it as latitude. And for the map title plus t, we want to say, okay, this is ATL14 ice surface height over Iceland. And then here we have a bit of an improvement over the previous map. So we've got like nicely labeled axis and like a map title. Then the next thing you probably want to do is what do the colors actually mean? Like, so when you're presenting data, you want to make sure that people understand what you're showing. And in this case, we're not sure what the colors actually mean. So let's add a color bar. So to add a color bar, we would use the fic.colorbar function. So if you don't give it anything, it will just plot the default one, but there's like different settings you can add. So if you click within the brackets, if you do a shift tab, it should pop up like a list of options you can go through. And so you can set like the position, the box, and things like that. But let's just use the default for now. And that should plot a color bar on the bottom of the map. And again, it's something, but we still don't know. Okay, what's 0, what's 2000? Like we need like sort of like units for this, right? So, and personally, I prefer elevation to be sort of as like a vertical on a vertical scale rather than a horizontal scale. So because like bottom means like low elevation, top means high elevation. So we can configure the color bar a bit more. So to do that, we can justify the color bar to the middle right. So set the position of the color bar. So we'll just justify it to the middle right side. For the gray values, we want to have like a box that says, oh, gray values are nan. Actually, nan values, they don't actually mean anything. So we can do a +n here. And then the color bar itself has a frame. So we can label the X frame as elevation and give it units, elevation in meters. So plus a label meters. And I'll just show you how that looks like. And here we go. So we've got a color bar right now to the right. It's got elevation. It's got a box showing what nan, that gray is nan. And it's got meter units. So this is kind of an improvement. But if you notice, we've actually got 2 color bars now. So if you go back, recall what I said about layers. So every time you're adding something to the plot, you'll be sort of drawing on top of the same plot. So if you want to make a new fresh figure, you would need to call fig equal pygmt dot figure again, and that would sort of erase what you've done, and you can replot the same thing. Okay, I know I've went through this very fast, but hopefully you can sort of play with this on your own time. And so we're going to take a bit of a short break, and I'll put a prompt in the tutorial prompts, and we're going to decide have a bit of a debate on what's the best color map, or like what's your favorite color map. I'll give you like 2 minutes to answer this. Okay. Yeah, magma, jet. Seriously, a lot of people like jet for some reason. Verdus, RD, red, yellow, green. Okay, polar. Yeah, so everyone seems to have an opinion on what's the best color map. So I'll tell you, like, so GMT has a lot of color maps. And if you click on this link here, list of built-in GMT color palette tables, you can see sort of some of the color maps GMT has by default. And is jet in here? Yes, jet is here. So we've got magma as well and all of that. And grayscale, of course, Scott, if you're after black and white images, there's grayscale as well. But one of the things that the scientific community hopefully is moving towards is these like sort of scientific color maps by Fabio Cremeri. And these are like perceptually uniform color maps, so they don't really distort the data as much. So when we visualize that, it's not distorting the data incorrectly, which like, so jet has a purpose. Jet can be used to reproduce old maps, but other than that, I would not suggest using jet for your next map anytime, please. Okay, So let's move on into the interest of time. So if you've decided on what color map you want to choose, you can change it here. So let's say, for the sake of it, why not? Let's do jet. So you can, use whatever color map you want here using the make CPT argument, or in this case, I would prefer FES, which is a scientific color map. So make CPT creates a color map, and you can sort of set the color map you want and sort of the series. So in this case, we want the color map to go from -200 meters to 2,500 meters. And so we'll need to change the GRD image call to use CMAP equal true instead of CMAP equal whatever. So before we were doing something like you can do like CMAP equal FES as well. But to have more control, you would use CMAP equal true, and that will pick up the color map made in this pygmt.makeCPT call. Cool. And so we've got like a slightly different representation, slightly different base map now with the FES color map. Oh, and we'll just add a color bar so you know what the colors actually mean. So right now it goes from 0, so the dark green color at sea level up to about 2,500 for an elevation for like the highest points on this sort of ice cap. Okay, I'll skip over the advanced base map customization, but you can click on these links if you want to know how to customize your map more. I'll just show you how it looks like. So you, things you can do is with this fig.basemap function, you can set sort of like grid lines. You can have like a north arrow. You can have a scale bar. So there's quite a few things you can do just with this fig.basemap function. And I'll leave it to you to click on these links to explore on your own time. But we'll move on to vectors, vector features. So to start off, we'll start with making a new figure. So by calling fig equal pygmt.figure. Next, we'll set just like a simple base map. So essentially just the region we want. So this is still Iceland. And a frame as well. Oh, and for the region, just note that pygmt uses minimum min-lon, max-lon, min-lat, max-lat. This is whereas like some other programs, CartoPy, they would use min-lon, min-lat, max-lon, max-lat. So this is just something to note when you're using pygmt compared to matplotlib. But let's plot that. Oh, and we're doing a coastline plot of Iceland. So we're just going to plot the shorelines and a low resolution version of the shorelines. If you want a high resolution coastline, you can use H instead of L. And that will give you like a higher resolution coastline. But right now we're just going to use L, a low resolution one for this example. Next, we'll need to I'll be teaching you how to plot some points. So for that, we're going to use ATL 11. So this is the land ice height dataset. So from Philipp's tutorial, you should already know how to use Open Altimetry. So if you go to the Open Altimetry website, you can click on a track if you want. So in this case, we're picking this track that crossed Iceland on December 20th, 2021. And if you click on it, it would say like it would give you sort of the track ID, the track number. And if you grab that track ID, you can set up an IcePix query object with that, which would pull down just that track ID. So this is how you would do it here. Oops. Oh, and because we're using like a different project, we need to sort of re-authenticate. Again, it's using your Earth data login. That should run pretty fast because ATL 11 is a pretty small data set. So this is just subsetting to our Iceland extent. And we'll download this to the temp folder. Oh, okay, download's complete. Right, so we'll load the ATL 11 HDF5 file using X-array open dataset again. So we'll just give it the file path. And ATL11 comes with three sort of pair tracks. So it's combined two of the, so if you recall, ICESat-2 has 6 lasers, and ATL11 sort of combines each pair into one pair track. So it's, you essentially have three tracks instead of 6. And we'll just be grabbing the middle one for this example. So we use group equal PT2, and that should give us this X-ray data set. So it has a longitude, that's a latitude coordinates, and then you might be interested in some of the other data variables. So it has like a corrected height data variable, a sigma error associated with that, and like a quality flag as well, and lots of attributes. So you can read through those at your own time, but we'll just be using like the lat and long for now. So to plot vector data, what we would be using is fig.plot. So fig.plot accepts, you can pretty much throw anything at it. So with this data equal data parameter, you can give it a shapefile, you can give it a NumPy array, pandas data frame, X-ray dataset, or even a GeoPandas geodata frame. So it's actually quite a powerful tool. But in this case, we're just going to use X and Y. So we can do fig.plot X equal the longitude of the ATL11 dataset, and Y equals the latitude of that ATL11 dataset. And we'll just color it light green for now. And that should show up on our map. Okay, it might be a bit hard to see because this is, by default, is quite like a thin sort of line. So let's change the style a little bit. So to do that, we can modify our fig.plot call. So again, we will be using the same X and Y and the same color, but we can set a style. So in this case, we'll be using a circle of 0.1 centimeters. And then just to sort of make know that, tell people that, okay, this is the track, what track this is, we can set a label for it. And this label will show up in the legend later on. So PyGMT has a fig.legend sort of call. And this one, by default, it will plot on the top right corner position. So if we just run this, you see what I mean. So now our ATL11 track has gone a bit, it looks a bit thicker now. And we've also got this like nice legend of, okay, so this is the track. And this is track 1358, PT2. So it makes a bit more sense on like what we're seeing now. Okay, and moving on to the next part. So text annotations. So quite often, like when you're plotting like a track like this, you might have like cross-section plot, and you would need to kind of know, okay, sometimes like if you're plotting like a transect plot, you would need to know, okay, where are you starting? Is it? So essentially, you just want to like label an A and B on this line, right? So you can do that using PyGMT as well, using fig.text. And just to start off, we'll just plot like the capital of Iceland. So I'm not sure how to pronounce this, Reykjavik, using fig.text. So you can give it an X coordinate and a Y coordinate if you know the position of the capital of the text. And you can set a font as well. So in this case, we're using a 16-point font. Oops. And as well, and we'll add like a little red square. So using fig.plot, we can set the X and Y coordinates of the capital, so exactly where the capital is. We can set the style. So in this case, S stands for square, a square of 0.2 centimeters. And we'll use the color red for this. So this is kind of how this would show up. So you can have the text and plot the sort of red square representing the capital. Next, we're gonna label this green line A to B. And I'll show you how to, you can customize your text a bit more. So again, we'll need the XY and the text label. And with the font, so PyGMT, you can specify the font as, so you can give the size, comma, and then the font style and the color. So just to show you what styles and colors there are. If you click on these links, so these are like the default sort of styles you can choose from. And these are like the list of colors. So it's a bit hard to see, but there's like, I don't know, a million colors in here, which you can choose from. Or you can just give it like an RGB value and it will work as well. But we'll just use purple for now. So right now you have an A to B plot. Next, so if you want to go crazy, like you want to label the oceans and stuff, you can give picked up text accepts like a list as well. So this is just how you would do that. So give it a list of X values, Y values, text labels, and so anything in the list will have the same sort of font. So we're labeling the oceans here and the 3 largest glaciers or ice caps on Iceland. And so this is just optional, but if you want to know how to add like an overview map, you can do it with the fic.inset and like a fic.coasting, and this would just add like a nice little overview map of it. So where Iceland is in the whole world. It'll be useful to like, yeah, because when you're like pretty zoomed in, it's a bit hard to see what's happening. And finally, saving the map. So let's put it all together. So we'll start with a blank new figure, and we'll do all the raster plotting first. So plot the grid, add the color bar, tweak the base map a bit. So this is sort of the raster base map we have. And next you can add the coastline, the ATL11 tract, the text annotations, and the overview map here. So if you just add them together, the final plot looks something like, right? Okay, yep, it looks something like this. So you've got titles, you've got X and Y axis, a color bar, pretty much anything you can want on a map or need on a map, yeah, you will have here. And to save this figure, we'll be using, similar to Matplotlib, a function called fic.savefigure. So you will just give it a file name. I would recommend saving to PNG for just like normal presentations or social media posts. And you can just set a DPI of like 300. For posters or like publications where you want like higher quality, I would recommend saving to a PDF. And maybe with like a 600 DPI resolution. And that should save it to, refresh that. Yep. So you should have like a map like this. So this, in this case, this is the PDF, the vector quality PDF map. So like the text remains text. So if you zoom in and out, it's like pretty high quality. Okay. And that's all for this tutorial, this part of the tutorial. If you want to know more of how to customize your map, you can click on these links. So there's a lot of tutorials on specific things you can do. So plotting like 3D perspective maps, for example, or making subplots like this. So there's like code examples you can sort of modify for that. Yeah, and that's pretty much it.